We'll be starting our new chapter, electromagnetic induction. That is the sixth chapter in this NCERT textbook. So, in the last two chapters, what we have learned is that a moving charge can create electric field. Sorry, magnetic field. Or current carrying wire produces a magnetic field around it. So that's how we have seen an intimate relationship between electricity and magnetism that we have already seen in the last two chapters. Okay, so but the question was arising after that. So we have seen that moving charges creates magnetic field. So the question was whether the reverse is true. That means whether moving magnet, whether a moving magnet can create electric field or electric current. Okay, so that was the reverse question. Just a minute. So the question was whether moving magnet can create electric field. I'm sorry, just a minute. My screen got freeze. I'll just.
This conference
So
will
what I
now
was
be recorded.
telling is that in the previous two chapters we have seen there is an intimate relationship between the electric current and magnetism, okay, or magnetic field. So automatically the question was arising that if moving charges can create magnetic field B, then is it true that varying magnetic field also produces electric current. Okay. So that means whether the reverse is true. So see, if this is varying electric field, varying charges or moving charges. If moving charges or current can create magnetic field, whether the reverse is true. Okay, this was the question. The question was being answered by famous experimentalists and physicists. There are two physicists at least. So one is Henry from USA, and another one, the genius physicist, experimentalist, Michael Faraday. Okay, Faraday from England. Okay, UK. So they answered this question. The answer is yes. And how do they do that? We'll see. They have actually carried out a series of experiments, okay, carried out a series of experiments, and by analyzing, they have arrived what is called electromagnetic induction, okay. By analyzing the results of experiments, they have actually derived, or they have found out that electromagnetic induction happens due to change in the magnetic field, okay, or by varying magnetic field. So we'll see the definition. The phenomenon in which an electric current is generated by varying magnetic field is called electromagnetic induction. So today we'll be discussing electromagnetic induction. We are studying, this is sixth chapter in your NCERT book. We're starting from today. So as I said, we'll see how Henry and Michael Faraday, they independently had done series of experiments, and by those experiments, how they arrived Faraday's law of induction. Okay, from the experiment, they arrived what is called Faraday's law of induction. So today, this will be our aim to learn what is Faraday's law of induction and how do Michael Faraday and Henry, by series of experiments, arrived this law, Faraday's law of induction. Okay, we'll see that. So let us see Michael Faraday and Henry's experiment. So they have done actually series of experiments. We will take three main experiments what they have carried out. So the first experiment is this is the first experiment, suppose. First experiment. XPT in first. So in this experiment, you can see that there is a coil of current carrying coil. So you can see there are many turns in that, and in that, in the beginning, actually there are no current actually. Okay, in the beginning there was no current. This is the scenario in between. So there was a simple coil. Okay, simple coil wire. Okay, and then the two ends of the wire of this coil, two ends of the wire of this coil are connected to a galvanometer. So this is G. G meaning is galvanometer. So you might be thinking, what is the role of galvanometer? We have already learned in our fourth chapter what is called galvanometer, moving coil galvanometer. The galvanometer can actually indicate the presence. So what it can do, it can indicate the presence of current. I am writing R. So current to the circuit. So what it does, generally you will see this kind of, so galvanometer has zero here, then like that 1, 2, 3, 4, 5 like that. There will be many lines over here. So there will be a pointer, okay, like this. Okay. So when there is no current through the circuit, the pointer will be actually pointing zero line. If there is some current, suppose plus I is flowing, some current I, so then it will actually deflect towards this. Okay, depending on the value, it will show the number over here. So if it is 5 ampere, it will show 5 ampere over here. Okay, it will deflect depending on the amount of the current. If it is minus, negative current, then this will deflect towards left. Okay, that means the job of this galvanometer is to deflect. The pointer is to deflect and tell you whether there is some current in the circuit. Okay, I'll just clean this portion so that you can visualize this figure nicely. Okay. So what has happened, in the beginning there was no current, no flow. So there, see, now I have one loop of wire, conducting wire, with which there is a galvanometer connected at its two ends. And then what I have? I have a bar magnet. You can see this is a bar magnet. So I have bar magnet. So now what I'm doing, this bar magnet keeping the north pole towards the coil, I'm just moving it. As you can see the arrow, I'm just moving the coil. As see bar magnet, I'm moving the bar magnet towards the coil. And see which pole I'm moving towards the keeping near the coil is the north pole. So when I'm doing that, see in the beginning it was at rest. It was at rest at a certain distance. That time there was no current, no deflection in the galvanometer coil. Okay, pointer. So no deflection means there was no current flowing. So what observation has been seen? See, what are the observations in this experiment? So when the bar magnet was at rest in the beginning, so I write Bm for bar magnet at rest as observation. So no deflection in the galvanometer coil. Okay, no deflection. I'm just writing simply no deflection. So this you have to mean that no deflection in the galvanometer coil. Pointer. Okay, no deflection in the galvanometer. Now I started moving it. So now what is happening? Bar magnet move. So what we see? Deflection. Deflection in the galvanometer coil. That means what? There is a current in the coil which is flowing. So if I speed up, or if I just further move and move near to the coil, further moving, or speed up, speed up, speed up the bar magnet. So what we see is more deflection. More deflection. Okay, more deflection. You can see. But again, when I just bring the bar magnet and keep just inside the coil like this, north and south, just keep at rest. Then also no deflection. If I keep it here, so what I see, no deflection. Okay, this is the case. Now if I move it back, if I take the bar magnet back, okay, towards this way, then deflection is shown, but opposite deflection, opposite side, opposite deflection. Deflection is seen, but in the opposite direction of the coil. That means what? In this case, when I'm just removing it and taking it away from the coil, so there is a current, but in the opposite direction. Okay, earlier when I was moving towards the coil, the current was supposed positive, that means in some direction, and when I am just taking it away from the loop, then I am getting negative current. That's why the deflection is opposite, as I said in the working principle of galvanometer in the beginning. So this is one. This is some observations. Another important observation is that if Bm is rest, at rest, bar magnet is rest, coil moves. Okay, coil moves. So in this case also we see deflection. Okay, deflection is seen. Understand? So what we have seen, when the bar magnet was at rest in the beginning, there was no deflection in the galvanometer. When the bar magnet is moving towards the coil, keeping north pole just in front of the coil, then the deflection is seen, okay, in the coil. If we speed up, or if we further moving towards the coil, we can see more deflection in the bar magnet. If we just just simply keep inside the coil at rest, then also no deflection. And opposite deflection is being seen when the bar magnet is taking away in the opposite direction. Then we see opposite deflection in the galvanometer coil. That means what? What is the conclusion here? So not only that, not only the bar magnet moves. So suppose bar magnet is at rest, and coil is moving. When the coil is moving towards the bar magnet, deflection is more. When it is moving away from the bar magnet, then deflection is less, but deflection is seen. So these are few observations we have seen. So from these observations, what is the conclusion? Let us see what is the conclusion. The conclusion is, just a minute. I hope some question is getting cut. I'll just take it inside. So what is the conclusion? The conclusion is that the relative motion between the coil and the bar magnet is responsible for generation of electric current in the coil. So this is a quick conclusion we can draw from this experiment. I hope you people are understanding. Okay. Even if we keep the bar magnet at rest, but coil is moving, or vice versa, coil is at rest and bar magnet is moving towards and like to and fro, then also we see there is a deflection in the galvanometer coil. But when both are at rest, there is no deflection in the coil. So what is the conclusion from there? Conclusion is that the relative motion between the coil and the bar magnet is responsible for the electric current, for the generation of the electric current in the coil. So this was the first experiment. Let us see another experiment. So in the second experiment, what we have done, what actually Michael Faraday had done is that this time he has taken two coils instead of bar magnet. So bar magnet has been replaced by another coil of small area. Okay, C1 has greater area and C2 has smaller area. So bar magnet has been replaced. Bar magnet has been replaced by this coil. Okay, C2. And in this case, you look that the coil C2 is actually connected to a battery. This is a battery. What it does, battery actually flows a current in this direction. So flowing a current in the coil. Okay, flowing a current. If you connect with the battery, you will see there will be a current flowing in the coil. So if the current is flowing in the coil, what happens? We have already learned current carrying loop can create a magnetic field at the axis. The axial magnetic field it will create. In fact, it will act as a dipole or a bar magnet. That we have learned in the fourth chapter and fifth chapter both. We have seen that a current carrying coil can act as a bar magnet, current carrying loop or coil. Okay, so that can act as a bar magnet. So in this case, what we have done, we have replaced the bar magnet with the current carrying coil. Okay, C2 and C1 was as it is. You see, the galvanometer was as it is earlier, as it was earlier. Okay. Now what happens? Now this coil, the second coil C2, is actually moved just like bar magnet. Will just move towards the coil and away from the coil, and just keep at rest and just keep inside this coil C1. Okay, and see what are the observations. Same observation, like same experiment we are doing and seeing what happens. I'm not writing the points. I'm just telling you that see the coil C2 is just moved now towards the C1. Okay. When they were both at rest, actually when both are at rest, no deflection. Okay, in the galvanometer coil in C1. Okay, there was no deflection in this galvanometer coil. Now when C2 moves towards, okay, C1, what you see? Deflection in the galvanometer coil, galvanometer pointer, okay. So we can see the deflection. But again, if you just keep inside this at this, then also there will be no deflection. An opposite thing happens when you just remove it. You just remove the coil or take it away. We see deflection, but in opposite deflection. Okay, opposite side deflection we can see. Opposite deflection in moving C2 away. Okay, when C2 is moving away. So these are the observations, more or less same observations you can see with the C1, C2 coil also. What is the conclusion here? Here also we can see the relative motion between the coil generates electric current. What is that? Relative motion between the coil generates electric current in C1. So that is what we can conclude from this. Okay, this was a quick conclusion from this experimental observation. Now again we'll have another experiment. Okay, this is actually confirming experiment. Look here, what happens? There are two coils C1, C2. We have kept as this. As C2 was connected to battery, now also it is connected to a battery. You can see this. Now also it is connected to a battery, and the C1 is connected to a galvanometer to just record whether there is a deflection or no deflection. To see that C1 coil is connected to a galvanometer, just like earlier. Okay. In fact, I am not describing this first setup. This first coil we are not describing at all. So we have just taken another coil C2. In the previous experiment we have seen there was no key. There was a battery, but there was no key in the earlier experiment. So now this is new here. Okay. So what is the new here? The key has been actually connected to C2 with the battery. So what is the role of this key? You look here, you can see I have a battery like this. Okay, I have a battery like this, and I have a key like this. Okay, this is the key. What is the role of this key? So when the key is actually tapping here, okay, if I can tap this and just these two, suppose A and B are connected to each other, then only current will flow. Otherwise, if it is open like this, then there will be no current flow. So this is the role of the key. That means the switch. The key means switch. Okay. So key means switch. So switch in the fan, like we have, like in every electrical instrument, we have some switch. So here the K is the switch. What we do with this switch? Look, in this experiment, what we are doing will be momentarily tap the key. That means what? When momentarily tap the key, so these two will be connected. So there will be a current. See, in the battery, suppose I apply some 5 ampere current, but from the battery, immediately current will not be 5 ampere. Just try to understand this. So I have a battery which can give or supply a current in the circuit of 5 ampere. But as soon as you tap the key or switch on the fan, okay, immediately speed will not be the high speed. It will slowly increase. But it will take very, very less time, obviously maybe less than a second. but it will take some time. So as soon as you tap the key, what happens? The current in this circuit will rise how from 0 to 5 ampere. But very quickly it will reach to this. Very quickly. But it will happen. It will not, as soon as you tap the key, current will not be immediately 5 ampere. It will increase from 0 to 5. But it will happen very quickly. Maybe of the order of 10 to the power 6 seconds, 10 to the power minus 6 seconds, 10 to the power minus 5 seconds, or 10 to the power minus 4 seconds. So which are very, very less. So within very less time, it will increase to a change from 0 to 5 ampere. That means as soon as you tap the key, there is a change in the current in the circuit. Okay, just remember that. So momentarily when you tap, you see that there is a deflection in the galvanometer coil. Okay, there is a deflection in the galvanometer coil when you tap the key momentarily. But if you tap and press the key continuously, then what you see? No deflection again. So there are two conditions when there will be no deflection. One is when the key is open, and the second is if you tap the switch and press for a long time. Press for a long time. So what you see? You see a momentary deflection and goes back to 0. Okay? Momentary deflection you can see in a fraction of second. Understand? Now what we'll do? We'll see if we just momentarily see we had tapped actually very quickly tapped. Okay. Now what we'll do? We'll just switch it off very quickly. Very quickly we'll switch off. Then what will happen in this case when switching off? Then see, switching off means current was supposed as 5 ampere. Now it will take some time, about that 10 to the power 4 second, or maybe 10 to the power minus 10 to the power minus 4 second, or 10 to the power minus 6 second, whatever it is. It will take very, very less time compared to our measurable time, obviously. Very, very less than, much less than 1 second. But it will take some time to actually reduce the current from 5 ampere to 0. So because of this, there will be a change in the current in the circuit momentarily. And we will see when we are switching off, also there is a deflection. But this time the deflection is in the opposite direction. Okay? This time the deflection is in the opposite direction. Okay, so what you see, just tap it, there is a deflection. Tap continuously, no deflection. Okay, there is no deflection continuously. Again, switch off. So momentarily you will be seeing deflection in the opposite direction, and thereafter it will come to 0 again. So these are few observations we have seen here. So what is what is the case here? You look in the previous two experiments, what we have seen relative motion between the two coils, and even before we have seen the relative motion between the bar magnet and coil. So in the previous two experiments, we had concluded that relative motion between coil or coil and bar magnet was responsible for the generation of current. Okay, this was true from previous, but in this experiment, what we see? We see that there is no longer relative motion is required. See, relative motion is not mandatory to produce electric current, right? Electric current. This is what we can see from this experiment. Just by switching off and switching on, we can produce an electric current in the C1 coil. So what we see from here is that not the relative motion. In fact, not the relative motion. It is the change in the current. Okay, change in the current in C2, which produces electric current I in the C1. This is what we have come to a conclusion from this experiment, that it is not the relative motion, it is a change in the current in the C2 coil, which is actually responsible for producing electric current in the C1 coil. That means what? What is the overall conclusion we can draw? Overall conclusion we can draw is that varying current okay, time varying current in this coil, we can see that creates current in C1. That is what you can see. But inside that also there are things we'll learn here. So the conclusion, this experiment actually concludes that not the relative motion, not merely the relative motion between the coil. It is a change in the current which is producing electric current in C1 coil. I'll just tell you one by one what is happening in each case. Look, I'll just go to the first experiment itself. Look what is happening here. It is actually, see, in this case what happens? See, north pole and south pole, you can see from this magnetic line. What are these called? These are called magnetic field lines. Okay, magnetic field lines. Look, this bar magnet is producing a magnetic field around it. Magnetic field around it. Okay, it creates a constant magnetic field around it. Constant magnetic field around it. Constant B. But when we are making it in motion, okay, when we are just making it to move towards or away from the coil C1, what is happening? The thing is that the number of field lines which are passing through this C1 coil is changing. Number of field lines, just mind this sentence. The number of field lines which are passing through this coil perpendicular to the plane of the coil is changing. Okay, this is what we can see. See, if we just bring closer and closer, what happens? Number of field lines will be increasing and increasing. That's why we will see more and more deflection. When we take it away, so it is going further and further away. The number of field lines which are passing through this coil will be reducing. Okay, and when it was at rest, suppose it is at rest condition, it is not moving at all. Then see, number of field lines which are passing through this coil will be constant. Understand? When bar magnet, okay, is at rest, what happens? Constant number of electric field lines, magnetic field lines, sorry. Constant number of magnetic field line will pass through C1. Okay. So when you hold them, both of them fixed, number of field lines which are passing through the C wall will be constant. If it was 100 lines, then it will remain 100 lines. But if you just move either of these two, then this number will change. It may change it to, it may reduce it to some 50, or it may increase from 50 to 100. Okay, just for an example. So this is what is happening. I'll tell you what does this mean. Number of field lines passing through a cross-sectional area means magnetic flux. What does it mean? That is actually called magnetic flux. Number of magnetic field lines crossing an area perpendicular to the plane of the area is called magnetic flux. Okay, this is denoted by phi and sometimes phi b. We'll see that. So what is changing is actually ultimately the number of field lines which are passing through C1 is changing. That means what is changing? It is changing is the flux. Okay, changing is the flux. We'll just come to the second experiment. Look, in this case also, when we pass a current through a coil, what is happening? It will produce a magnetic field around it. Okay, it will produce a magnetic field around it. So which is shown over here. You look here. Okay, it will create a magnetic field around it. Okay, and if we move again this one or maybe C1, either of these two coils, if we move again the same thing, what is changing in the number of field lines which is passing perpendicular to this plane of this C1 coil is changing. It is not the relative motion alone. There is a physics behind it. So the coil C2 is creating magnetic field, and when you are keeping the C1 at rest, you are moving C2 coil. The field lines which is passing through the C1 coil is changing. Okay, that means flux is changing through flux. See, number of field lines passing through the C1 coil is called flux link. The number of field lines which are passing through the C1 coil is called flux link. Okay, flux. Sometimes you will come across this flux link. Sorry, link. Flux link. The link flux will change due to this relative motion. Okay, so this is what in this case also. Now come to the third experiment. What happens here? In this case also, look, when the current is actually, in this case current is varying. Current is varying. So I is varying here. We have seen that if you send a current in a coil, it will produce a magnetic field. Again, if your current is varying, then B also will vary. This also will vary. If B is varying, then the flux link, also will be varying. Okay, and it is momentary because when the current is changing, then only B will be created. See, B will be created always. If a constant current also flows, B will be created. But when I is varying, see, when we momentarily switch on, then only I is varying. So I is varying when upon switching on or switching off. Otherwise, when it is continuously switching on, then the B is constant. Okay, B is constant. That means number of field lines which are passing through the C one coil, because they are not in a motion now, both are fixed. So that will be actually constant. Okay. So this is what we can see from both the experiments. Okay. So varying current, in this case, varying current will create a varying magnetic field in the third case. So what we'll see from all the experiments, what we see from all the experiment is, what is the conclusion? The varying magnetic field actually creating varying magnetic field, or okay, magnetic field, or we can say uh, change in the flux. What we say? Change in the flux. Change in the flux. What flux? Change in the magnetic flux. Okay, magnetic flux. You have already learned what is electric flux. The same definition here also, magnetic for magnetic flux. So change in the magnetic flux produces what it produces? It produces electric current. Actually, it produces EMF, and that EMF produces current. Okay, it produces varying flux. Actually, produces EMF, electromotive force, and that in turn produces electric current. Okay, produce electric current. Okay, we'll see that. Just before we analyze that further and derive simple mathematical formulation given by Faraday for law of induction, we need to know what is called flux. So as I have already told, if you have an like area like this, suppose this is a perpendicular area like this. Okay, suppose this is an area which is perpendicular to the magnetic field line. Okay, so the number of field lines which are passing across, okay, passing through them. You can see this figure. Magnetic field lines are passing through that, okay, but not normally. They are not actually. See, this is B, so it is not passing perpendicular to the area. So that's why in this case, the definition of the flux, magnetic flux, phi B, has to be written in this way: B A cos of theta. If A is the area vector, okay, look, area vector and magnetic field vector, they have angle between them is theta. This is the magnetic field vector, and this is the area vector of the loop. So when my B is perpendicular to the area, that means B and A are parallel. When B is perpendicular to area, okay. Now, but there is an angle now here, okay. The area and magnetic field, they are not perpendicular to each other, so that's why you have to find out the angle between area vector, which is the outward normal to the area of the surface. So you will get this one. Okay, this is a scalar quantity, and this is called magnetic flux. And this magnetic flux is denoted by phi. I'll write once again phi B A cos theta. And if you want to write in terms of vector, notice and then B dot A. Okay. So this has unit. This is called magnetic flux. And it has unit Weber. Okay, Weber. Since this is Tesla, this has unit meter square, so it can be written as Tesla meter square also. Okay, Tesla meter square. That's why this B has another unit, phi B by A. This has another unit, Weber per meter square. Weber per meter square. B has another unit, that's why it is called magnetic flux density also. So B is called magnetic flux density also. We have already already discussed this. So this is called magnetic flux density. That means magnetic flux per unit area, as you can see from here. Okay, magnetic flux density also, Ω per meter square. So B is called even magnetic flux density, which is called magnetic flux per unit area, and it has unit Ω per meter square. And this flux has unit Ω bar. You can find out the dimension, like, okay, dimension. If you know the dimension of B and A, then you can find out easily what is the dimension of phi flux. Okay. So now look, what was the conclusion? We had concluded that the time rate of change of magnetic flux in the circuit induces electric current. And Faraday, from this observation, Faraday had given a simple mathematical expression for the experimental observation, that is, that the time rate of change of the flux, okay, flux in the circuit induces an electric current, and before that, obviously, there is EMF actually induces an electric EMF which creates a current, which produces current, which produces electric current. Okay, so mathematically, if we want to write that, so EMF will be denoting by this, and this is actually, the EMF is directly proportional to the time rate of change of magnetic flux. That is what Faraday has told or suggested. And if you write in terms of equation, there will be minus sign over here, and d phi by dt. Okay. So this phi b we know b a cos theta. Okay. Now, if you have only one term from this case, if you have n number of terms, so you will get plus n b a cos theta. So in that case, you can write, see, I can write d dt of n b a cos of theta, and you can just do the derivative and get, like, this kind of things will come in when you go for numerical problems. So you can just this NBA and cos theta will be sin theta. Okay, sin theta, and then obviously this will be d theta, dt will be multiplied. Dt will be actually angular velocity, and if you put that, you will get n b a omega sin theta. Okay, if your coil is rotated, so we have seen in the previous slide that you have phi b is ba cos of theta. So if you want to increase or decrease this flux or change the or vary the flux, there are few parameters, like 3 parameters, 1, 2, and 3. Either you can vary the magnetic field, which is not so easy. Okay, changing the area, easy, and even changing the relative orientation of the magnetic field and the loop, that is also easy. Okay, you just take a magnetic field around this way, and they just take a circular coil like this and just rotate it. Just rotate about this axis. Okay, then you know if this is the normal for this area of the loop. If you rotate it in this way continuously, it will change its direction. Okay, that means flux will change, and if the omega is the velocity of rotation, then we can write the flux in this fashion. Okay, we can write the flux in this fashion. Okay, so we can write the flux in this fashion. So the EMF will get actually the plus NBA. And so this is called EMF, electromotive force. So which is the source of current again. So this EMF actually produces current, electric current. So about EMF we have learned already in third chapter, I guess. So EMF produces electric current. So I hope you understand what is the origin of electric current produces in the coil, so that you can see the deflection in the galvanometer. So that is the EMF which is getting induced. So this EMF is called induced EMF. What is this called? Induced EMF. Because of rate of change of the flux. The time rate of change of flux is producing an electromotive force or EMF, which is called induced EMF, and that induced EMF can be obtained by laws of like Faraday's law of induction. So I'll write in clearly. So this is the Faraday's law of induction. This is called Faraday's law of induction. In fact, Faraday had given up to here, like this is directly proportional to this, and this sign was given by Lenz, German physicist Lenz. This sign is actually giving you the direction of the induced EMF. What is this giving? It is giving the direction of induced EMF. So this sign gives the direction of induced EMF in the coil. Of induced EMF in the coil. Okay. So this is the sign is given by scientist Henry Friedrich Lenz. He is a German scientist. Okay. He's a German scientist, Germany physicist. He had given the law, or this is called Lenz's law, where he has given the sign of this induced EMF. Faraday had given this actually. So induced EMF will be directly proportional to the time rate of change of the flux linked in the coil. Okay, this is Faraday this has been given by Faraday, and this sign has been given by Lenz, and this Lenz. This is Lenz. But if you are asked to write the Faraday's law of induction, you should not write like this. You should write complete law. Okay, this is not complete law. You have to write with the sign. Okay, but in fact you can write this. After writing this you can write this is Faraday's law of induction. You can in fact write that this is the sign which is giving the direction of the EMF induced in the coil, and this sign is given by Lenz. Like that you should write in the exam. Okay. So all right. So let us see. Okay. Okay. So it is already the time. What we'll do in the next class, we'll learn what is Lenz's law and how Lenz's law give the proper direction of this induced EMF, and from there, like how the Lenz's law is satisfying the conservation of energy. We'll learn this thing in the next class. Okay, so thank you for your patience. Pujita and Guna, you are. So I hope you people have understood up to what I have discussed. Faraday's law, up to Faraday's law of induction, we have discussed today. So you people should read that so that you can understand the things clearly. And then next day we'll learn the Lenz's law and conservation of energy. How Lenz's law is satisfying the conservation of energy. Okay, I'll stop it here today because if I start, it will go another 15 minutes. I don't want to extend up to that. You may have also some other class. So thank you, Pujita and Guna. I will meet again on Wednesday and we'll discuss this. So electromagnetic induction is very interesting topic. If you can learn it, you will again enjoy the classes. Okay, please read up to what I have taught you today, so that you can understand the rest of the portions. Okay. All right. I'll stop it here today. Good night.